everyone, welcome back to the Secrets of Calculus. We've got a lot of big braining coming up, but this will give us the tools to solve nearly every derivative. Hang on, is this video too long for you? Here's the formulas. Let me know what you did with that extra free time. And yeah, that's a lot of formulas. So first up, let's review our problem. We have an alpine slide that is boring and dangerous because it works entirely in straight lines. But at least we could tell how fast we were going at any point in time. We brought in the functions e to the x, x squared, natural log of x, and sine of x to smooth this out, but now we don't know how to measure the speed. Luckily, speed is related to the slope of a line tangent to the function at one point. But wait. You need 2 points to make a slope. But wait. We can use a limit to pretend that we have 2 points until we use algebra to make it irrelevant and then pretend it was 1 point all along. Just like this. So, this is great and all, but how do you actually, quote-unquote, take the derivative? We can use the limit definition on, let's say, f of x equals x squared. One tricky part in all this is remembering that the x is here being squared, turning into an x plus h. But now, we can just compute this limit. We can't just plug in h equals 0, so we need to do some expansion first. No, not that kind of expand. Like this. So we have a plus x squared and a minus x squared, which annihilate each other. And okay, we're still using our convenience ability to say approaching 0 is not the same as equaling 0. So we can simplify by dividing by h. And now, thank goodness for a limit, because now we use our convenience power to say approaching is the same as equaling. Boom, we just plug in h equals 0. And we get our answer. The derivative of x squared is 2x. Which I will write for now as 2x to the 1 for future purposes. Cool, right? And remember what the derivative did. We can plug in any x value to get the slope of the tangent line at that point. So if we plug in, say, x equals 0, we get 2 times 0 equals 0. A slope of 0 is a straight horizontal line, which is exactly what we would expect at a vertex. We can do the same thing for something like x cubed. I'm going to super speed this one. Boom! There we go. The derivative of x cubed is 3x squared. You might be able to see a pattern already, but let's ponder what you get for a function like 1 over x. It can also be rewritten as x to the negative 1. Here's what happens. Now this answer can also be written as negative x to the negative 2. So here's what we have. Do you see a pattern? It's okay if you don't. Here's what the pattern is. It makes sense, right? The exponent hops down in line and then decreases by 1. And with this, we can also take the derivative of a constant. Let's call this constant c. Fun fact, constants can also be written as c times x to the 0. And when we take the derivative, we get c times 0 times x to the negative 1. But then we're multiplying by 0, so this gets 0. So when we take the derivative, we lose information about where the function was. That's going to be important later. Also, this means we can't get x to the negative 1 as an answer. At least, not with this method. Hey, you know what would be a really convenient? A function whose derivative is itself. That would be really cool, and I think we can generate a function like that. We did see behavior like that with functions from before, like x squared at x equals 0. Except that only works at x equals 0. Plug in 1, you get a function value of 1 but a derivative of 2. That's no good. Let's pull out a mathematical toolbox and see what other functions we have. Aha! We have functions like 2 to the x. The behavior is that the value of the next integer is 2 times more than the value of the previous integer. These are called exponential functions because the x is in the exponent. These are perfect candidates since the growth rate depends on the function value. Now what would happen if we took the derivative? Let's use the limit definition. We can use some exponent rules here to try to simplify. And since the limit only cares about h, we can factor out 2 to the x. Now, this limit is what makes things interesting. For one thing, plugging in 0 gets a 0 divided by 0 undetermined situation. Later on, I'll show you how to deal with a limit like this, but for now, we don't know any big braining tricks to work with it. But we can always brute force it by letting h get really, really small, which is what we'll do here. Okay, this limit is definitely approaching something. What that number is, who knows? But we can see that our closest estimate, the derivative of 2 to the x, is about 0.693 times 2 to the x. Okay, let's try the same tactic with the derivative of 3 to the x. It's the same algebra, so I'll super speed through it. And once again, we'll brute force this limit by letting h get really small. And this limit is also definitely approaching something. So the closest estimate for the derivative of 3 to the x is 1.099 times 3 to the x. Okay, we're getting somewhere with this. The derivative is one of these functions is itself. But there's this multiplier here that messes things up. In order for the function and its derivative to equal, we need this multiplier to equal 1. So, we need some number, let's call it e, where the limit as h approaches 0 of e to the h minus 1, all that over h, equals 1. And some smart guy from 300 years ago named Euler found this number. It's about 2.71828, and actually it continues infinitely with no pattern, just like pi. So there we go. The derivative of e to the x is e to the x. And while we're at it, we can see that to get the derivative of any exponential, like 2 to the x, we multiply by the natural log of the base, which is 2. And its natural log is about 0.693, which perfectly matches our brute force limit. While we're at it, let's also find the derivative of the logarithm function. Since e to the x was such a nice function, we can expect that its inverse, the natural log of x, would also be fairly nice to work with. Let's use the limit definition once more to find this derivative. Oh boy, this limit is even more unruly than the exponential limit we had from earlier. We're going to use a logarithm trick that states that we can turn this difference into a fraction inside the log. And now, to proceed further, we need to introduce a new variable, u equals x divided by h. Substitutions like this can be done anytime you want to any equation, but you have to be able to replace everything you're targeting, which in this case is h because the limit is only concerned with h. Since h is in the substitution, we need to change the limit as well. As h approaches 0, we know from before that u would approach positive or negative infinity. Now, since the logarithm function can't handle negative numbers, we'll work with the positive infinity answer. So here's the limit. One last log trick, we can turn a multiply by the log into a thing inside the log to that power. Yeah, you can probably see where this is going. Since x is not considered for the limit, we can just move it out. And now we use a limit trick. The natural log function is continuous for any positive number, so it will definitely exist at u equals infinity. Using this, we can sneak the limit past the natural log. Hey, we know how to do this limit. This is one of those special limits, which equals e. And lastly, e to the x and natural log of x are inverses of each other, so the natural log of e is 1. And there you go. The derivative of the natural log of x is 1 over x. If you wanted the derivative of a log base other than e, you can use a log trick that changes the base like this. Now, this works for any base a. We'll learn how to deal with constant multiples of derivatives, but for now, you'll have to trust me that since we know the derivative of natural log of x is 1 over x, the derivative of this log base a will be 1 over x times the natural log of a. Phew, that was a lot to cram in, but there's still more. We still have to meet up with Chief SOHCAHTOA to complete our utility belt of everyday functions. Then, we can add dips and bumps into our Alpine slide. See you next time!